balls. It seems I got a white ball and an 8 ball, and you can't tell that it's an 8 ball, but it's a cue ball and an 8 ball. If you're into playing pool, that means something to you. And the white ball is in motion, and the 8 ball is just sitting there, the black ball. But of course, if you're playing billiards or snooker, that 8 ball is usually sitting still when that white ball is moving. And we could talk about momentum, but momentum is always conserved. But as we've said before, energy is not always conserved. Oops, out of focus. Within the system. And when we talk about conserve, we mean for the whole system. So any system that loses energy, which is most systems, is said to be inelastic. And we have these rare other kinds of systems that are purely, depending on who you're talking to, purely, or I would think most people would say perfectly, elastic systems. Are exceptionally rare. Put like an exclamation mark there because it really doesn't happen very often that a system has exactly the same energy before and after. I think about like situations where that could happen. It might happen in particle physics if you don't have any light emission, or you can take stock of the light emission when particles decay, or the radiation emission as particles decay, but it really doesn't happen very often. Anyway, I want to say that we've got a perfectly elastic collision, that word perfectly. After a collision, perfectly inelastic collision. After the collision, and this is kind of just like a definitions thing, energy is lost. And so we might talk about two objects traveling towards each other. In the before scenario, and then in the after scenario, it's possible that actually it's not possible. In this situation, not only do they collide with each other, but they actually stick together and they travel together afterwards. And if I wanted to like picture this in like a macroscopic way, think about like if you threw two Play-Doh balls at each other, and in midair they stuck together, but then the larger of the two Play-Doh balls had more momentum, and they stuck together and traveled in that direction. Obviously, it would be at a diminished velocity relative to the original Play-Doh ball. I mean, if it wasn't Play-Doh you want to play around with, maybe trains. And two trains were heading towards each other, and they stuck together because there's like a locking mechanism or something like that. Then afterwards, they'd still be stuck together, but they kind of travel in one way or the other, depending on who wins the tug of war, the momentum battle, if you like. Anyway, so we're going to add that into this. After the collision, energy is lost, and after the collision, energy is lost, and the objects stick together. Exclamation mark, because that's a big idea, that they stick together. Perfectly elastic, or completely elastic, or purely elastic. I've seen it those three different ways. The total energy before and after is the same. Total energy of the system before and after is equal. And I'll just say it again, super rare. And so we might be talking about, you know, theoretical pool balls that are traveling towards each other, and then they bounce off of each other, and the total kinetic energy afterwards is equal to the total kinetic energy before. Super rare. If you really wanted to like eliminate all the energy loss, maybe we wouldn't even talk about like classical pool balls. Maybe we could load these pool balls up with like a magnetic force field or something like that, whereas they come towards each other, they repel off of each other's force fields. You know, like that could be a thing to try and eliminate energy loss. But like you would really have to contrive things, right? All right, so partially elastic or partially inelastic. And actually, I've seen people do this kind of thing with magnetic hockey pucks. You can actually make like a magnetic hockey puck and send it towards each other. Partially elastic or partially inelastic, because being partially elastic or partially inelastic, I've even seen people say not perfectly elastic. Synonymous things to say. This is what we're saying is some energy is lost, and just to make sure we're clear about this, but not destroyed, because it's usually being dissipated as heat or sound or one of those things, but they bounce off each other. So we're distinguishing ourselves from the first one because they don't stick together. And so it might look very much like our second scenario where these two objects are on a collision course and they may bounce off of each other, but with a diminished total kinetic energy for the system afterwards, right? We're kind of losing energy somehow. So I got these two cars that are on a collision course, and we could say that if momentum 1 equals momentum 2, because I've got mass 1 and mass 2, we know that there would be a full stop collision. This would be if they have the same magnitude of momentum, but they happen to be going in opposite directions. That's a situation that could happen. Other things we could talk about could be, you know, like relating to these three definitions that we have up at the top here. Let's talk about how they could relate. So we could say momentum total is equal to momentum total primed. Fair enough. And we could expand it out. Mass 1, because I've got mass 1 there, V1 plus mass 2 V2 equals mass 1 V1 primed plus mass 2 V2 primed. But let's just say that this time we want to think about what was happening in this first situation up here. We want to say that afterwards this system sticks together. So if the system does stick together, let's just say but the two cars stick together after the car crash. So we say V1 primed equals V2 primed. It might be just be easier to lump those two together as the same variable because it's all going to stick together as one like ball of car metal. So we could say, let's just call that V primed. And that's if it's perfectly inelastic. Perfectly inelastic. So that first scenario, that first definition up there at the top, the perfectly inelastic situation, this would be true. So I might want to rewrite it like this. I might say M1V1 plus M2V2 equals, if this is going to end up being, you know what, I'm going to use my whiteout. That means that V1 primed and V2 primed are going to be the same value. So I'm just going to call them V primed. But as I notice that, I say, you know what, I could factor V primed out of that binomial and get V primed is equal to, or sorry, V primed times M1 plus M2. Now, for whatever stylistic reason, see how we got the binomial of m's in the end and the V primed at the beginning? People like the masses to be up front because that's how we've conceptualized momentum. Like people always write the masses up front. So people don't typically write it this way. Sometimes you'll see people writing M1 V1 plus M2 V2, and then they'll kind of weirdly write M1 plus M2 times V primed. I'll put that V after the binomial. It operates the exact same way with the distributive property, so don't stress about that, but just puts the mass up front. I'll put a box around that. And I want to call this equation A. I'm calling it equation A, but I want to put the letter A right up here beside my terms list. Now situation, well, I'll just say it's situation B. In situation B, I want to look at a perfectly elastic scenario. And if I was going to look at a perfectly elastic scenario and consider energy conservation, I would say 1/2 m1v1 squared plus 1/2 m2v2 squared is equal to 1/2 m1v1 primed squared plus 1/2 m2v2 primed squared. And remember, that is really rare, but I'm going to put a box around it because that situation I'm going to call situation B, or equation B. That fits with my terms list right up there. I'll put the letter B next to that situation. Perfectly elastic, super rare. We have this system of equations that governs these kinds of interactions. The next one that I might look at is a perfectly inelastic or partially elastic energy conservation. So, or partially, so not perfectly elastic energy conservation statement. If I'm talking about that, I would make an equation that would look like this. Well, I mean, the before energy looks like this. I'd say EKA, I won't expand it out as 1/2 mv squared, EKA plus EKB equals EKA primed plus EKB primed, which is essentially exactly what I said right up here in the previous statement. But to balance both sides, because energy is going to be lost in both these situations, we would write it as plus energy lost. So that the right side really does equal the left side. So the difference between the right side and the left side is the energy loss. I'm going to put a box around that one. I'm going to put a C. Now, a quick little extra on this. If it's specifically for the perfectly inelastic situation, so actually, you know what? I should go back up here and I should put the letter C next to this one and the letter C next to this one. Then I got to come back down here and say, you know what? I do want to come up with a letter D, but the D in this case would be really similar. EKA plus EKB equals, remember, in the perfectly inelastic situation, the objects stick together. So since they're sticking together, we could write it like this: 1/2 m A plus mass B, because they mash together and become essentially one object, times V primed of that mashed up single object squared plus E lost. So I'm going to call that equation D, but it kind of acknowledges that this equation D really is equivalent to equation C, except we're kind of recognizing that the two masses become one. So I'm going to go back up to perfectly inelastic and say that I got equation D here. But then throughout all of these, and we're just going to wrap this up really quick, no matter what, P total equals P total primed, which means that we will always be able to say that we have equation E, mass A VA plus mass B VB equals mass A VA primed plus mass B VB primed. Now the reason that it's nice to have these systems of equations is just like in math class, when you have a system of equations, you can solve, when you have two equations with two unknowns, you can solve for those unknown values. So we're going to treat this as systems of equations, very much like math class. We're going to follow this up next time, okay?